workshop. Today is the 13th. Happy almost Valentine's Day. Okay, so what was I know I looked at it, but uh-huh. Uh-huh.
And then the limits are x equals 0 and y equals 0, those are your boundaries. And we are revolving around y equals 1.
So here's our region. And we're revolving around y equals 1?
Yeah.
Okay, that's going to be interesting.
I'm pretty sure it's y equals 1.
Okay. So if I'm approaching, oops, let me do one thing here.
It is y equals, wait, no, sorry. It is also limited by y equals 1.
Okay.
And revolve around
Okay. Revolved around y equals 0. Okay, so I'm going to try and sketch the region a little bit. It doesn't be perfect. The only thing that's hard to draw here is e to the y squared, e to the y squared, e to the y squared. So if I'm thinking of it really as y equals e to the x squared, which kind of does that, but then it kind of does the other thing. So if I was graphing this, I would say, well, if y equals 0, then x equals 1. And then as the y values get higher, the x values are going to get larger, right? Right. So when y equals 1, x is going to equal e. Now that has to be perfect. We try and do a decent job of graphing the thing. So it looks like my region is looking like this. That looks terrible. And we're revolving around the x-axis. Okay, I don't think, well, I don't imagine we're going to have to break this up into two intervals. But I'm not sure. So if I'm going around the x-axis, well, no, I'm not going to say that. If I have a region, an area that I want to try to find the volume of, right? So volume, revolve this one. I'm going to draw a strip that makes the most sense to me. And if I'm James looking at this, what kind of strip am I going to draw? A horizontal or a vertical one? Show me with your hands. Give me a vertical hand or a horizontal hand. Right. I'm going to draw a horizontal one because the horizontal one, well, actually for two good reasons, I would say. The main reason being it's the same throughout, right? No matter how high or how low this thing slides, it's the same right boundary of e to the y squared. It's the same left boundary of 0. The other reason this is a good choice is because we've already got functions of y, right? We could certainly solve this for y as a function of x, but I really don't want to have to do that if I can not. So usually sticking with the way your functions are defined is also kind of a good reason to do it one way versus the other. So if I'm going to set this up, I'm going to be using, well, since my strip is parallel to my axis of rotation, we know we're using the shell method. And the volume of my shell is 2 pi r times the height times the thickness. Right? This little strip has a thickness of dy. It's got a height of, or length of however long it is, which is just the right function minus the left function. So the height there is going to be the right function e to the y squared minus the left function, which is x equals 0. And then the radius, oh, this is going to work out great. The radius is going to be what? How far is this strip from the axis of rotation? Y, indeed. So the volume here, total, is going to be the integral of 2 pi y times e to the y squared dy. And my limits of integration are going to be from as low as y equals 0 to as high as y equals 1. Which is not terrible at all, right? This is kind of like an ideal situation. If I put the pi out in front, just to make it look even a little more obvious, we can write this as pi times the integral from 0 to 1 of 2y e to the y squared. And the integral of that's e to the y squared, right? I think we can all see the u substitution here. U would equal y squared, du would be 2y dy. This works out perfectly. I don't even want to write it down. I'm going to say it's pi times e to the y squared from 0 to 1. So we end up with pi times e to the 1 minus e to the 0, or pi times e minus 1, which is hopefully correct. It is not correct. So I will point out, books have mistakes. Let me look at the question one more time, just to make sure we're not missing a really important fact.
Who use just pi?
Huh.
And that's why it's a little bit weird.
Problem 13.
Yeah.
Volume of a solid generator when the region found x equals e to the y squared. And the line is y equals 0, x equals 0, and y equals 1. But no, I think they're right.
Okay.
So yeah, so sometimes books have mistakes, which is good to be aware of, because sometimes it can be really frustrating if you think you're doing something right and it's not coming out the way the book has it. So just it's not something you should, like, if you do it wrong, or if you think you've done it wrong and you check and you're like, it's good to check again or ask me. But like if you've done it a couple of times and the book is and like you've cited some sources and talked to people, then you might have to think, well, maybe the book's wrong. You could also plug it in Desmos. I didn't know. I saw the thing you showed me. You can do integrals on Desmos.
In Unpack, it's just command key.
Oh, cool. I didn't know that. You can do integrals on Desmos. That's cool. Good to know. I learned something. All right. So let's talk about moments, which we just started to talk about last time, but then had some technical difficulties and we decided to stop. We moved this too much and the plug came out and I couldn't tell what was going on. So, moments. Yeah, I should just draw the full picture again. So, when we talk about moments, we think about a force being applied to a lever arm. I know. I remember what I was doing last time. I was trying to show everybody the door over there so that they could talk about how if I applied a force far away from the fulcrum, it moves the door pretty easily. But if I apply the same amount of force much closer, it doesn't move the door hardly at all because my lever arm is much less. So the torque generated by this force applied to this lever arm a certain distance from the fulcrum is greater the larger the distance. In other words, I always have to be super careful here because I tend to write things. I tend to have a not great conceptualization of how this all works. So I'm giving you my best, but if you really want to talk to someone about this, you go talk to Duff. Duff, the physics guy. If you're taking physics, ever you should, we have, right, you guys, I should say, hopefully everyone's aware that the AATC doesn't have just math help. There's chemistry, and physics, and all kinds of other stuff. So if you have to take physics at some point, I highly encourage you to take the physics co-classes or workshops or whatever they're called. I took them when I was a student. They were super helpful. Physics 9 is a hard series. I recommend getting help with it. That said, back to this. So very generally, a moment is a mass times the distance to the lever arm, or sorry, distance to the fulcrum, apologies, which we typically call which I typically refer to as the lever arm length, or just the lever arm. And when we start thinking about the center of mass, we really want to think of it as a balancing point. So here's one way to kind of conceptualize this. Where should, as an example, an opposing 10 kilogram mass be applied for the following system to balance, but does not rotate? So here's the system. I've got some fulcrum right here. I'm gonna have all this mass on this lever arm to the right. So let's see, where have I got things here? Pen color. I have 1 meter out. I have a 5 kilogram weight, or sorry, mass. Another 3 meters beyond that, I have a 3 kilogram mass. And another 6 meters beyond that, I have a 2 kilogram mass. And the question that I'm asking is, where would I have to apply an opposite mass times lever arm force so that this system would balance? So where am I applying this 10 kilograms of mass times how far away it is? We're just finding the center of mass. But the way I'm talking about it in this way so that we can have a better idea of what it really means. So to balance this, to find the balance point, we want all the moments to add up to 0. We want the sum of the moments to equal 0. Which is not too hard to calculate. So again, very, very generically, moment is mass times distance from fulcrum. So I'm thinking of all of these red masses here is going to be giving me a positive moment. So I'm going to say that my moment here is going to be 5 kilograms times 1 pound, well, times 1 meter. This is 1 pound. Plus 3 kilograms times 4 meters. Plus 2 kilograms times 6 meters. Plus negative 10 kilograms times however far this is, which is what I'm trying to actually find, which we typically call X bar.
Yeah, this is 3 meters and then 4. Oh, because it's the 1.
Right, because so this is 1 meter from the fulcrum, 4 meters from the fulcrum, 10 meters from the fulcrum. Oh, I wrote 6 though. Thanks. Good call. Right on. Yeah. Other questions, observations, mistakes, anything? All right, and we want this to equal 0. And I should point out, these are all positive because they are interesting. I'm thinking of it that way. Huh. I'm thinking of this as being counterclockwise rotation. Right. I'm thinking of these as like pushing this lever arm down that way, and this one pushing it back up other way. Oh wait, getting my clockwise and counterclockwise backwards. I'm so used to thinking of counterclockwise being positive because of how we think about angles, right? Counterclockwise is usually positive angle measures. That when I wrote it this way, I just automatically, my brain was like, oh, counterclockwise clearly gotta be positive. So, but no, here we're thinking of going this way, which is positive, which is clockwise. Right? That direction is clockwise. That's our positive. So these are all positive because clockwise. And this one is negative because counterclockwise.
You still get the same thing if you made all of those. Because negative and that one positive.
Yeah, you would. Yeah. You're asking a question I'm not equipped to answer. I really don't like the physics for me is shaky. I'm not gonna lie. Like I don't have a good conceptualization of what torque really is. I know there's something about how the right hand rule or maybe the left hand rule interacts with torque, but honestly, no. Torque is unfortunately something I'm just not that good at really knowing about. I guess I could learn it, but I don't want to. So anyway, calculating this, 5 times 1 plus 3 times 4 plus 2 times 10 is 5 plus 12 plus 20, which is 37. And it's going to equal, if I add this to the other side, 10 times X bar. And I could throw out some units here, but I don't really need to. These units over here are kilograms times meters. These units over here are kilograms times meters. And when I divide by kilograms, I'm going to get meters. So I end up getting that X is equal to 3.7 meters. I should really say X bar. 3.7 meters. So what we're saying here is that this distance being 3.7 meters is where it balances. Something that I think is worth doing is if you actually recalculate this with that being where you put the fulcrum, you'll get a moment of 0. So just to kind of revisit this, because this kind of always confused me when I was a student, is if instead we think of our system, the same system, but now with the fulcrum actually being at 3.7 meters from the end, so it's 6.3 meters from the other end, then this 2 kilogram mass is 6.3 meters from the fulcrum. This 3 kilogram mass is just a little to the right of the fulcrum. It was 4 meters away from the end, so it's going to be 0.3 meters from where I've placed my fulcrum now. Well, because it was, so I said that the center of mass was 3.7 meters from, essentially we're thinking of this as x equal to 0, and this is x equal to 10. So if I've moved it over 3.7 meters, I've essentially just done 10 minus 3.7. And really here, this one that was at 4, I've really just done 4 minus 3.7. And this other mass that was 1 meter over, maybe like right here, that's my 5 kilogram mass. This one is located 2.7 meters from the fulcrum, but it's to the left, so we're going to count that as negative, right? Because that's going to make it go, oh my God, counterclockwise, and that's going to make it go clockwise. So check this out. If we sum the moments, well, the moment for this is going to be 6 times 6.3, plus the moment for this is going to be 3 times 0.3, plus the moment for this is going to be 5 times negative 2.7, and it exactly comes out to be 0. I feel like I've made a dumb mistake somewhere, like really dumb. My brain's not, because so what I'm saying is this should come out to 0. It does not look like that's going to come out to 0. Oh, that's because I wrote down the wrong mass somewhere. Right, it should be 2. I definitely made a dumb mistake right there. That thing should be fine. So 2 times 6.3 is 12.6, 3 times 0.3 is 0.9, and 5 times 2.7 is 10 plus 3.5, which is 13.5, and that's exactly 0. So if you actually look at the moment around your center of mass, the moment around your center of mass should be 0. But what's nice is that we can calculate it really easily by saying that the center of mass is just the sum of the moments divided by the total mass, or the sum of the masses. Why? Because we are thinking about, and that's why I did this, right? We're thinking about where an opposite amount of mass would have to be applied to counteract the moment going this way. So the moment going clockwise in this example, when the fulcrum's here, is exactly 37. And we want the moment going counterclockwise to be the same, and we're going to use the same amount of mass and just figure out where that mass has to be applied so that the moment in the opposite direction balances the moment in that direction. Yeah. And then we can make this more complicated, as we always do, right? We start off with an easy example, and we try to make it more complicated. So we can say something like, what if instead we want to find the center of mass of the thin rod whose length is 10, centimeters, with a density of delta equal to x squared grams per centimeter as measured from the origin, or from the left end. So the idea here is that we're taking this thin rod that's 10 centimeters long, we're just placing it along the x-axis. And just like before, the center of mass is going to be the total moment divided by the mass. Well, the mass is changing, or I should say the density is changing, which means that, right, this, like this little section here has less mass than this next section here. And so to do this thing where the mass is changing as a function of x, we're going to end up having to integrate, of course. So what we're going to do is we say, well, we're going to do the integral of whatever the mass is times the distance to the fulcrum. Just like before, mass times distance. And the bottom, total mass. But again, if your density is changing, we have to do an integral to find the mass. All right, so if we think about a little segment here, right, this is going to equal, so the mass of some little segment, well, the density is x squared, and the width is dx. Sorry, my picture is looking messier every moment I look at it. So the mass is going to be x squared times dx. Density times however much of it you have, which might be a dx, which might be an area, which might, it depends on what kind of thing we're looking at. But in this example, our amount of stuff that we have is just the length dx, because it's a super thin rod. Doesn't really have any area. It's fine. And then we're going to multiply that by the distance to the fulcrum, which is x, over the integral of just the mass of that little slice or strip or segment. Okay. Oh, and then my limits of integration are from 0 to 10. That's how long the rod is. So here we're integrating from 0 to 10 of x cubed. Here we're integrating from 0 to 10 of x squared. We're getting x to the 4th over 4 over x to the 3rd over 3, both from 0 to 10, which comes out to be 10 to the 4th over 4 times 3 over 10 to the 3rd, which is 3/4 of 10, which is 7.5. So our center of mass is 7.5 centimeters from the left end, which again seems reasonable because the thing is denser the further right we go. I should mention, because it's often a point of confusion, this center of mass point, 7.5 centimeters from the left, doesn't mean that half the mass is over here and half the mass is over here. It means that this is the balancing point. You could think of it, although it's kind of weird to say, you can think of it as half the moments over here and half the moments over here, or the moment on that side and the moment on that side are balancing each other out. But again, it's not how much mass there is, it's how much moment there is.
That's always the equation for the center of mass is nova over mass.
Yeah. Not. Well, and so I mean, we can even calculate it, right? The integral from 0 to 7.5 of x squared dx is going to be 7.5 cubed over 3. And that's not going to be the same as the integral from 7.5 to 10 of x squared dx, which is going to be 10 cubed over 3 minus 7.5 cubed over 3. Those are for sure not the same. Well, but so again, right, the center of mass balancing point isn't where you have half the mass on one side and half the mass on the other side, because what if half the mass on one side was really close and the other half the mass was really far away? That further away mass has a greater moment, and we're trying to find the place where the moments cancel each other out. So the moment is 0. Okay, so
If you know the things that have like weight in each side, would the center of mass be when it's like equal, like it's not moving?
yeah.
Okay.
A common thing to think about, and actually this is literally the same kind of idea. You all know how to find an average, right? And I think we talk about this later. But so when you find an average, you're not finding where half of the data is on one side and half of the data is on the other side. You're finding a weighted average, right? The outlier is way, 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 way out. bump the average up. Like if you talk about, it's kind of why we use median household income as a measure of household income versus average household income. If you did average household income as a measure of average income, the people making billions and billions of dollars would stretch that average up. It would really, really make it look a lot higher than which is what the actual measure of the center would be. And so they are kind of those people making lots and lots of money. Those are the people that have a really large moment. If we're thinking about it in terms of moments, if we want the moments to balance, right, we'd have to find the actual average versus a better measure in this case, which would be the median. So again, not a perfect example, but kind of gets the idea that, right, it really matters not just how much area is on either side, but also how far that area is from the middle.
Is X bar the center of mass?
Yes. So I should say, if we're looking at something that's in one dimension, yes, X bar is the center of mass. And then when we look in 2 dimensions, we'll call it X bar, Y bar.
And also the question would tell us when the fulcrum isn't at.
So there's it's really more of a way of visualizing things. So we're always thinking of the fulcrum as being at the origin, or if it's 2 dimensions, the x-axis and the y-axis, because that's how we talk about it. But then usually, like, my imagination goes to then saying, well, once I find where the center of mass is, that's where I'm really imagining my fulcrum would be if it was to balance on the fulcrum. But yes, you're right. I might be saying too much. Yes, we're always doing it around the y-axis and the x-axis. So it's always the distance from those things.
Okay.
You can talk about moments around other lines. It's a giant pain. We usually don't. Right. I mean, it's not a terrible pain, but right, just like how finding the volume of a shape around another axis, you have to change your radius by either subtracting one from the other. You would do the same sort of thing to find the moments around a different line. So if I want to find the moment, well, in fact, let's look at a new example, and then we can briefly address that kind of special situation. So let's look at an example in 2 dimensions. Let's say we want to find what I'm going to call the centroid, which is just the same as the center of mass, except we assume constant density. Of the thin plate pictured below. Of the plin plate? No, I try and combine thin and plate together, you get plin. Of the thin plate that looks like this. It's bounded by y equals x and y equal to the square root of x. We want to know where the center of mass of this shape is. And that's kind of, yeah. So for plates, or for regions in 2 dimensions, our center of mass, or centroid, if we assume density is constant, is going to be x bar comma y bar, where x bar is the moment around the y-axis divided by the total mass. And y bar is the moment around the x-axis divided by the total mass. If we think back to our previous example, this makes perfect sense, right? When we were finding x bar, the x coordinate of the center of mass, we took the moment around how far it would have been from the y-axis. In fact, I think I even drew a y-axis, right? Right, we were finding how far we were from the y-axis here. So I just want to make sure you don't get it kind of twisted up, because it can be really confusing. People are like, wait, x bar is my over mass? Yes, it is. X bar is my over mass. The moment around the y-axis, the likelihood to swing around the y-axis divided by the mass. Because we're trying to find the x coordinate. Okay, so just like before, moments around axes are just how far you are from that axis times how much mass is swinging around that axis. So if we think about a vertical thin strip, we're going to say, oh, well, that thin strip is a distance of x from the y-axis. And it's got an area of top function minus bottom function. So here are my is going to be the integral of our mass of our strip times our distance, which is going to be, so the mass of that strip is just the area times the density. And the area of that strip is dx times the difference in the functions. So it's going to be the top function x minus the bottom function x times the density times our x times our dx. Which I know looks a little bit terrible, but really it's just area times lever arm. Oh, and then limits of integration from 0 to 1.
Is that the density symbol?
Yeah, delta, lowercase delta. Which we don't really need here, but I want to show you why we don't need it, so I'm leaving it for just a second.
What exactly is my and mx?
So my is the moment, good question, yeah. My is the moment about the y-axis. And similarly, mx is about the x-axis. So calculating this, we get the integral of the delta out in front. X times x to the 1/2 is x to the 3/2. X times x is x squared. We integrate, we get 2/5 x to the 5/2 minus x cubed over 3, 0 to 1. And we end up getting delta times 2/5 minus 1/3, which ends up being 6/15 minus 5/15, which is 1/15 times delta. Okay. In the same way, we can find the moment around the x-axis. Now, here's something, and this is where things start to go kind of sideways. If, whoops, not my, mx. If you can find mx by doing the same sort of thing, I highly encourage it. Meaning, I would prefer, if I could, to use a horizontal strip. And I totally can. The mass of that strip is just its length, but now I'm doing things in terms of y. So I'm going to say the length is, well, x equals y minus x equals y squared times the thickness times the density. So there's the mass of my strip. I'm going to multiply that by how far it is to the axis I'm going around, which is now the x-axis. So that distance is going to be y. Go from 0 to 1 because, right, this end point 0, 0, this end point's 1, 1. So doing that, we get the integral from 0 to 1 of y squared minus y cubed times the density, which I should just put out in front, which ends up being density times y cubed over 3 minus y to the 4th over 4, 0 to 1, which is the density times 1/3 minus 1/4, which is 1/12. Okay, and then finally, the mass, which maybe we should have found first. That's just the integral of the area. It's just really just the area times the density. So I'm just going to do the integral. Either way, I might as well do it kind of the first way. From 0 to 1 of the square root of x minus x times the density. No lever arm though. Question.
You said that square root of x minus x times the density is the area, but then you and the bottom.
Sorry, you're right. Yeah.
Is that mass?
It's mass. But now it just looks like a mess. Literally, actually.
Is the dx is because that the square root of x minus x times dx, that's the area, right?
Yes, exactly.
Yeah,
Yep.
okay,
And so then the area times the density is the mass. Same deal here, right? The area times the density is the mass. And then here, I'm just integrating the mass, right? It's the area times the density, no lever arm included to find the mass. When I do that, I end up getting, let's see, x to the 3/2 times 2/3 minus x squared over 2 times density. From 0 to 1 is going to give us density times 2/3 minus 1/2, which is 4/6 minus 3/6, which is 1/6. Okay, here's what's nice when you're finding something with a constant density. The densities are always going to cancel out when you're finding the centroid or the center of mass. My x bar is going to be my over the mass, which is my delta times 1/15 over my delta times 1/6. Those deltas definitely cancel. And so you end up getting 6/15, which reduces to 2/5. In a similar way, my y bar, which is the moment around the x-axis, which was 1/12 y, or I should write it, which is 1/12 delta over the mass, which was 1/6 delta. Deltas cancel out again, and you just get 6/12, which is 1/2. So the center of mass, x bar, y bar, is 2/5, 1/2.
Because I'm thinking if you, because the average of this in calculus is a to b of f of x over the interval, you might say. Are you talking about-
That's a different thing. So that is the average value of a function. That's the average height. Where if I want to find the moment of a function, I would have to integrate x times f of x. So essentially, it's the idea of taking like each value and multiplying by its probability and then adding all that up.
Probably the distribution function, the center mass of that would exactly be.
Yeah, exactly. Yeah. Okay, cool. So the reason this is nice if you can do it this way. The moment around a particular axis is just how far it is to that axis multiplied by the mass of your strip. Now, what people typically end up doing here is you just say, I don't have to worry about the delta, right? If I wanted to find the centroid, you're welcome. For the centroid, which is just also x bar, y bar, it's just going to equal my my over the mass on my mx over the mass. But then you can kind of get rid of the density. So really you're just saying it's really going to be the integral of x times whatever your function is, dx, over the integral of your function. And then same deal for the y's, for the mx. Mx is going to be the integral of y times your function over the mass. Which you probably wouldn't do a different way. I don't mind writing it a different way. Okay, so here's what's kind of funky though. It's totally fine, assuming that you can totally find all your functions in terms of either x or y, which is you probably are aware is not always true. We can't always write our function, right? You can't always take your function of x and solve it for x in terms of y. Not every function is invertible. Additionally, if someone said the mass, or should apologize, the density is variable, then you might be stuck using a particular variable anyway. Let me show you what I mean. So let's find the center of mass for the following plate. Given that the density at any point is equal to x squared. So meaning the further right we travel, the denser the object is. It doesn't matter how high up or how far down we are. I mean, here's my plate. It's going to be the region bounded by y equal to 2x and y equal to 3 minus x squared. Oops, 3 minus x squared. Oh my gosh, can I write? Maybe. And then x equal to 0.
For the last problem,
Mhm.
we were assuming that density was constant. Would that just be like just a numerical density?
Right. So density would be like 5 grams per square inch or something.
Oh,
But the next thing is specifically when you're calculating the center of mass or the centroid in that case, the densities just cancel out. And so typically, if someone says assume the density is constant, you can either not even think of writing it or just assume it's 1. On the other hand, when the density is variable, we are in a less good situation. So I want to find the center of mass of this. Same as before, a little bit. So the mass first is the integral of the area times the density. The area, oh, no, that's mass, right? I'm not doing moments yet, I'm doing mass. No lever arm yet. So again, I'm just gonna use a vertical strip. The area of that strip is height times width. So I'm really just gonna get my area being 3 minus x squared minus 2x, all times my dx, and then also times my density, which is x squared. From x equals 0 to probably x equals 1. Yeah, that's the point 1 comma 2. Right, that's x equals 1, yeah. So multiplying this out, we get the integral from 0 to 1 of 3x squared minus x cubed minus 2x cubed dx. And that ends up being x cubed minus x to the 4th over 4 minus 2x to the 4th over 4, which is x to the 4th over 2 from 0 to 1. 0 to 1 is kind of the best ever. It's really just your coefficients if your powers of x. So we get 1 minus 1/4 minus 1/2, which is 1/4. Which I feel like, did I make a mistake? Gosh, what? It should, God, man, I apologize. It is not on top of it. Sorry. Good call. Thank you. That should be an x to the 5th over 5, which means we should actually be getting 1 minus 1/5 minus 1/2, which is 10/10 minus 2/10 minus 5/10, which is 3/10. And then, yeah, we got enough time. Okay. To find the moment around the y-axis, same as usual. We're going to find essentially it's the same integral as before. You're just tossing in a lever arm. So the length of my lever arm is just x if I'm going around the y-axis. So my moment from around the y-axis is going to be the integral from 0 to 1 of that same integral from before. 3 minus x squared minus 2x times x squared times dx if you like, right? All of that's my mass part. And then we're multiplying that by the lever arm mass. I know I don't love putting stuff after the dx, but it's fine.
Oh, what do you mean by lever arm?
I mean, if I think about this strip, I'm thinking about how far it is from the axis that we're going around. So lever arm, you can also call it distance to the axis we are talking about. But often it's called a lever arm because you're thinking of like the weight actually being on the end and then kind of like moving it around. So it's like the lever arm. So then if we multiply this out, being a little more careful than last time, we should get the integral from 0 to 1 of 3x cubed minus x to the 5th minus 2x to the 4th dx, and then integrating, we get 3x to the 4th over 4 minus x to the 6th over 6 minus 2x to the 5th over 5 from 0 to 1, and that just ends up being the coefficients again. So it's 3/4 minus 1/6 minus 2/5, which is something probably heinous. 60, I guess they're common denominator. So we get 45 over 60 minus 10 over 60 minus 24 over 60. And that's what, 11? Yeah, I think. Let me double check. Yep, 11 over 60. And then just to kind of, since we're already there, our x bar would be 11 over 60 divided by 3 over 10, which ends up being 11 over 18. Now here's the sad news. The other integral is harder. Because we can't do the thing we did last time. If we're going around the x-axis, we can't write things in terms of y because our density is in terms of x. Right, there is no way of saying density equal to x squared changed as a function of y. It's x squared. You can't do anything with that. So what we have to do is kind of this weird following thing, where we say we're going to use what is typically the alternate formula for the moment around the x-axis. So here's the idea. If you have some sort of shape that's very general, just for a second, and we're taking kind of a quick little trip here, and this top function is f of x, bottom function is g of x. We're still going to use a vertical strip because we can't really use a horizontal strip if we have to do things in terms of x. And the idea is that we're going to say, well, this rectangular strip, we can imagine all of its mass centered at its center of mass. So we're going to say all of the center of it is just right there at its centroid, right? That's the thing about nice shapes that have symmetry is if density is constant. And as far as this strip is concerned, since density only depends on x, if we're saying all this strip is like the same x, its density is constant as far as we care. So if the density is constant, you can kind of pretend that all of the mass of this strip is centered at its center of mass, and rectangles, their center of mass is just, if the density is constant, where the center is. Same is true for circles, same is true for triangles. So if you have shapes that have nice symmetry, you can often get away with saying, oh, well, I know where some of the center of mass is because it's balanced on the other side. So that's a useful piece of information, which we probably won't say too much about today, next time. But here what we're going to do is we're going to say, well, all of this mass, the mass of our strip is still just top function minus bottom function times dx times the density. And then the lever arm, well, if we pretend like all of the mass is in the middle, it's just how far this is. And that middle of these two functions is the average of those two functions. So the lever arm is going to be f of x plus g of x divided by 2. We're imagining that all that mass is right there, halfway between f of x and g of x. Okay, and then if you multiply these together, look what happens. You get, now let's write it this way. So if you do mass times the lever arm, writing it a little bit more nicely, you're going to get f minus g times the density times your dx times 1/2 of f plus g. People then usually simplify this because f minus g times f plus g is f squared minus g squared. So people typically find the moment around the x-axis this way as 1/2 the integral of f squared minus g squared. Don't forget the density. I forgot the density. That is the alternate formula for the moment around the x-axis. It's kind of terrible. Here's the good news. When you get to 21D, the formulas get a lot nicer. If they talk about it at all. So if you're stuck with having to use a specific variable, like you just can't use y for whatever reason, then if you have to use x and you're going around the x-axis, this is how you calculate the moment. So back to our example. Sorry, no, I apologize. I tried to squeeze it in there and it was not good. Density times f of x squared minus g of x squared dx. So back to our previous example, our moment around the x-axis is going to be 1/2 times the integral from 0 to 1. And then our top function was, what was it, 3 minus x squared? Yeah, it was 3 minus x squared. Oh, don't forget the density. The density was x squared. And the top function was 3 minus x squared. And we have to square it minus the bottom function, which was 2x. And we have to square it. which is a little gnarly. I mean, it could be worse. It could be 1/2 integral from 0 to 1. We multiply this out, we get 9 minus 6x squared plus x to the 4th. My nose really itches all of a sudden, sorry. Minus 4x squared. Multiplying that through, we get 1/2 integral from 0 to 1 of 9x squared minus 10x to the 4th plus x to the 6th. Seems good. We integrate, we get 9x cubed over 3. We get the 1/2. We get 10x to the 5th over 5. Oh, that comes out nice. You too. And we get x to the 7th over 7 from 0 to 1. So we end up getting 1/2 times 3 minus 2 plus 1/7, which is 1 1/7 or 8/7. So 1/2 of 8/7 is 4/7. Whew. So then our y bar coordinate would be our mx over the mass, which is 4/7 over our mass, which I forgot was what, 3/10. That ends up being 4 over 7 times 10 over 3, which is 40 over 21. Wow. So a couple things about these is they're usually very calculation intense. It's a lot of just like throwing a bunch of stuff into an integral, and even though it's not mentally challenging to do this integral, it is mentally challenging to keep track of all the pieces to make sure that we don't make a dumb mistake by multiplying x squared by x squared and getting x cubed. So word of advice is, if you have to do these problems, just be careful with the details. Yeah. And then just to point out, because I want to say one last thing just to make your life a little bit easier, if you have to say find the centroid of something like, say, y equals sine x, or the region between y equals sine x, y equals 0, from x equals 0 to x equals pi. I just want to point out that this region, we know what sine looks like. Looks vaguely like that. You already know where x bar is, because this sine function is definitely symmetric from 0 to pi. So although I don't know what y bar is, I definitely know that my center of mass, x bar comma y bar, I'm 100% confident that the x coordinate is pi over 2 by symmetry, because this thing has as much mass on the right of that line as it does on the left of that line, because the density is constant. I should also say, if it was variable density, all bets are off. You can't use symmetry really. Well, that's not entirely true. It's hard. Go ahead. Y bar, you still have to do all the normal work. So for y bar, we would have to find the moment around the x-axis divided by the mass. And here you are also stuck using that kind of terrible formula, because you could really, if you really want to make your life suck, rewrite this as x equals arc sine of y and integrate that. We don't want to do that if we don't have to. Here we definitely should use the alternate formula for the mass and say that the moment is 1/2 the integral from 0 to pi of the top function squared minus the bottom function squared. I didn't even write the density because the density is constant. And then the mass would just be the integral from 0 to pi of sine of x dx. And very soon we'll talk about how to integrate sine squared. Well, you actually know how to integrate sine squared already. Just have to use a trig identity. Sine squared x equals 1 minus cosine of 2x all divided by 2. That's how you deal with sine squared. All right, I should stop talking. It's 2:04.